Welcome back, everyone. Now that we understand the theory and intuition behind logistic regression, let's switch gears and actually implement logistic regression with Python and scikit-learn. In part 1, we're just going to be performing some exploratory data analysis to understand the data set we're working with. Let's head over to the notebook. Alright, here I am at the notebook, and the data we're going to be working with here is just some experimental data that was conducted on 5,000 participants, and it was mainly to study the effect of age and physical health on hearing loss, specifically the ability to hear high-pitched tones. So this is essentially some patients that had two features to them: their age of the participant in years, and then some sort of physical score. Essentially, they had a physical exam, and depending on how they performed on it, they reached some score. And then the label or target was 0 if they did not pass the test, that is the high-pitch hearing test, whether or not they could hear those high pitches, or 1 if the test did pass. So what we would like to do is later on have a new patient come in where we only know their age and then the score achieved on that physical exam, and then we could predict whether or not they are going to have some sort of high-pitched hearing issue, 0 or 1. That way we can just save ourselves the test, also based off the probability. So if we're pretty sure that they're going to pass the test, maybe we don't need to actually test them. Okay, so let's go ahead and just explore this data set. I've gone ahead and imported NumPy, Pandas, Seaborn, and Matplotlib.pyplot, and now let's read in the CSV file. We'll say pd read CSV, and I'm going to do this under the data folder that comes with the course material. There is a CSV file called hearingtest.csv. You should be able to just auto-complete this with tab. So again, under the data folder, depending on where your notebook is actually located, you may have to provide the full file path or 2 dots here to go back up a directory. Right now, I'm underneath the logistic regression models folder, so that's why I have these 2 dots to go back up a directory. So read that in, and let's check the head of the data frame. This lecture is just going to perform some exploratory data analysis so we understand what's going on, especially because we haven't actually performed any sort of exploratory data analysis on a classification data set. So typically, for a classification data set, your target variable is going to be in 1s and 0s. Sometimes it's in strings, which you can just easily one-hot encode or integer encode to test results with either a map or apply, etc. Something that's typically important is to understand what the 0s and 1s mean. Almost always you'll have some sort of description here, like 0 if no pass or 1 if test pass, but sometimes you'll be reading in a data set from an unknown source, and you always want to clarify what the 0 means versus what the 1 means. Okay, and later on we'll discuss multi-class classification. So we have some ages, we have some physical scores. Let's go ahead and describe the data. We can say df describe. Run that, and now I can see the general distribution of these data scores. I can see the mean age seems to be 51 years old, physical scores 32. I can check the minimum and maximum of the physical scores. So it looks like the physical scoring goes from 0 to 50. So on a 0 to 50 scale, the average person is getting about a 32 physical score. And we can see that the ages, the minimum age is 18 years old, and the maximum age, the oldest person in the data set was 90 years old, mean person is 51 years old. And then these statistics for the test results are a little harder to interpret because they're just 0s and 1s. So really, we don't really care about the mean or standard deviation too much. Instead, it's probably better just to get value counts for them. So let's go ahead and do that. I can see df test results column and get the value counts. So you run value counts, and this will tell you that there's 3,000 people that passed the test and 2,000 people that did not pass the test. And we can also do a Seaborn count plot. If you ever need to visualize this, you can just pass in test result here, run that, and it will show you the test result. Keep in mind the way I just ran this is I just passed in that series. Later on in future versions of Seaborn, you will have to be a little more explicit. You have to say something like data is equal to df, and then x is equal to the column string test result, and then that's how it's going to be in the future. So keep that in mind. You won't be able to conveniently do what I just did. You'll have to actually split it up into 2 sets. So what would be interesting for the next step is to actually see the distribution of the features per category. And we know that box plots are a good way of visualizing that. So let's say box plot, where I'm going to check the test result against the age. So we'll say y is age, and then my data is df. And so what this is going to visualize for me, we can go ahead and create a figure object here just to up the DPI a little bit. So we'll say DPI is, let's say 150, make it a little sharper. There we go. So the kind of questions this answers is there a difference between ages and the test result? And here we can clearly see a difference in the distribution. What this is showing you is that people who do not pass the test, that is a 0, tend to be older than people who do pass the test. And in general, that makes sense. It makes sense that the older you get, the less likely you're going to be able to hear those high-pitched values. Let's see if there's a relationship between that physical score. So we can come back up here and change Y from age to the physical score column. So this is the physical fitness of someone, and let's see the relationship here. And again, this is actually an even sharper contrast. So it looks like you have a really wide distribution on the physical score for people that don't pass the test. However, if you have a very high physical score, it's extremely likely that you're going to pass the test. So notice here again the distributions of the physical scores for people that pass the test. They all tend to be scoring really high physically. So that could also then be a relationship between physical score and age. So let's actually see that relationship. I'm going to say SNS scatter plot, and we'll say age versus the physical score. So we'll say data is equal to DF. Run that, and what do we see here? We see that as your age increases, your physical score tends to go down. So kind of obviously a linear relationship here. There's definitely some noise, but the trend is very clear. The younger people tend to have a very high physical score, and then the older you get, you tend to have a lower physical score. And what you can actually do is then visualize this with the test result. So you can add a hue. So we can say hue is equal to test result. And when you run that, it's going to essentially color the points. And keep in mind, some points are stacked on top of each other here, so you may need to start adding in an alpha to really start to clarify things. So we may also want to up the DPI on this one. So I'm going to copy this and paste it in here. So upping the DPI, dots per inch, and let's also put this on 2 lines here. Let's also add in some alpha as something like 0.5. So we run that. And so now I can see points that are stacked on top of each other. And here we can clearly see 2 groups, 2 clusters where we have this high physical score, younger people passing the test, and then these older people, or even some younger people with lower physical scores that are not passing the test. So this is to be expected. Our intuition is basically confirmed here that if you're younger and in more or better physical condition, you're more likely to be passing this hearing test. Okay. So last plot we should probably be doing here is something like a pair plot or heat map. So what we can do is just say SNS pair plot, and I would always recommend that you do this, especially for classification, because it's so easy to do on a small data set, is you just pass in the data frame and then say hue by test result. And this is often the very first plot I usually do, because it basically shows the information that we just did versus separate plots. So we can see the distributions of age and physical score between the 2 classes. Clearly, physical score, big indicator here, and I can also see the scatter plot we just created. I can also create a heat map of how correlated the features are. So I can say heat map of DF correlation, and then what you probably want to do is also annotate this. So annotation is true. Run that, and you can see just how correlated everything is. So you should always get a 1 along the diagonal because every feature or label is perfectly correlated with itself. And then you can see here that you have these high correlations between passing the test and your physical score being higher. And then age, you can see a negative correlation because as your age increases, you're less likely to pass that test. Okay. The last thing I want to show you here is that sometimes when you're dealing with classes, scatter plots don't really work too well if one of your axes is going to be based on the class. So let's show you some scatter plots that are not too informative sometimes, and then show you how you could use a 3D plot, depending on how many features you have, to try to clarify that information. So we go back to scatter plot here, and we did a scatter plot of age versus the physical score. Those are 2 continuous variables. But what happens if we actually do a scatter plot where one of the variables is going to be a label, just 0 or 1? So I could say x physical score, and then let's say y is that test result. and data is equal to df. So I run this scatter plot and I get something that looks like this. And this may or may not be informative. Obviously it depends on the actual data set. But we can see here, this is almost more like a box plot than it is an actual scatter plot. And so if you get something like this, I would recommend that you probably actually use a box plot, because this is essentially just showing you the distribution of the physical score per class, which is pretty much exactly what we did if we come back up here with what we did right here. You'll notice that this is showing the same effect, where people with that did not pass the test have a wide range of physical scores, and people that did pass the test tend to be really high physical scores. And that's the same information that's being shown here. It's just showing you with dots. The last thing I want to point out here is often when we're dealing with smaller data sets that only have a few features, we can take advantage of that and actually view things in 3D. But the question is, how do we actually create a 3D projected scatter plot here? Well, what you can do is simply do a Google search of something like 3D Matplotlib scatter plot, and it should take you to a bunch of links, but we have the link in the official documentation in our lecture notebook, or you can just check out the 3D scatterplot link inside of Matplotlib's official documentation, and it shows you this basic construction of a scatterplot in 3D. And if you take a look at this, it might look like a lot of code, but you'll soon notice that much of this code is actually just for creating that random data set. So the first thing you have to do is say from mpltoolkits.mplot3d import axis 3d. So I will go ahead and copy that, and let's put that right here. And then let's continue through the code and see what we need and what we don't need. This import matplotlib pyplot and np, we've already done that. We actually don't really care about creating the random data, so I don't need to make a seed. And you notice this is a helper function to create those random numbers, so we don't need that either. And then we have the creation of the figure and this adding of the subplot with the projection equals 3D. So let's copy these two lines because they are also important. And then we'll put those in. And if we come back to that documentation page, you'll notice that this is actually a for loop just for creating the random sets of data in X, Y, and Z. And then it finally creates a scatter plot of those arrays. So how about this? We'll just actually copy the scatter line, since we don't actually care about creating the random data sets because we already have the data. So I will copy this and then bring it back in here. And now I just need to replace my X's, Y's, and Z's. So what I can do here is say that my X is going to be equal to the age column. My Y is going to be equal to the physical score column. So we'll say physical score. And then my Z's here should be the final column we have, which is the test result. So we'll say df is equal to test result. And I actually don't care about this marker M, because if we look back here, marker M was just this dot versus this triangle. So I can get rid of marker M. And if you just run it like this, you'll notice that we essentially have these two clusters, which is the 3D projection of the scatter plot here, along with another feature. And we can actually color this based off df test result with the code we actually already know, which is C is equal to df test result, and that will color everything. So right away you should notice that there's clear separation between people that did not pass the hearing exam versus people that did pass the hearing exam. This means the model should be able to score very well on this actual classification task. So let's go ahead and explore how we can set up the data and train the model in the next lecture. I'll see you there.